So, in the seminar what I shall try to do is to introduce a probably new concept, that of interpenetrating potential energy landscapes. Now, we have already had 4 lectures on PELs. Unfortunately, I had to miss that because of prior commitment. I do not know if any of these lectures mention the word interpenetrating potential energy landscape. If they have not, I claim that this is a new concept. And I will try to present examples of occurrence of interpenetrating potential energy landscapes experimentally. And I will try to show that one of the consequences of this form of potential energy landscape interpenetration is the reentrance of glass transition and supercooled liquid state. And my experimental technique I am going to use, or I have used and present here, is the technique of spin probe electron spin resonance. Now, electron spin resonance of course is a very well known and old technique applied to many different areas of science. I understand that in this school so far there have not been any lectures on electron spin resonance or ESR as an experimental technique. I understand that later next week Professor Egami is going to talk about nuclear magnetic resonance. I do not know if there is any talk on electron spin resonance, I presume not. So, what I will do is I will spend a few minutes on explaining the basics of this technique. So, the outline is here. First, I will spend a few minutes on the technique of electron spin resonance, and then give examples of spin probe electron spin resonance in supercooled and glassy water, of glass transition in water, and then SPSR evidence for reentrant glass transition and supercooled liquid state of confined water. So, first, because ESR seems to be a strange technique to this audience, I thought I would do some motivational sales talk taken from this fairly recent paper of D.L. Griscom, where he talks about one bad day 65 million years ago. I am sure you all know what this bad day was, where either a meteor, giant meteor, or a comet hit the earth in Mexico that led to the extinction of the dinosaurs who ruled the earth till then. And at the same time, lot of matter evaporated and got quenched to form glass. And Griscom studied this glass extracted from the crater in Mexico by the technique of ESR. And he says that paper describes one human scientist's utilization of an experimental technique, electron spin resonance, that he once applied to borate glasses to help answer the question of what became of the dinosaurs. Again, to summarize, in an instant of geological time, the earth became blanketed with more than, this is 10 to the power 16 kg of glass. Another example of application of ESR was to the glassy samples obtained from lunar rocks, again done by Griscom, where he studies using ESR the magnetic particles impregnating the glasses obtained in lunar rocks. And coming back to the present day, these are a couple of our own works where we claim that we provide some additional insights for vitrification and glass transition of water using SPSR, and more recent work where we claim again providing evidence for the two coexisting liquid phases in deeply supercooled water. We are very thankful to Professor D. Leporini of University of Pisa for having collaborated with us on this work. As you know, as you probably know, Professor Leporini has been one of the pioneers of the application of ESR to the study of supercooled liquids and glasses, especially to the problem addressed in the previous lecture of decoupling of viscosity and diffusion coefficient, again using the technique of spin probe ESR. Now, it turns out that ESR is particularly useful where the conventional technique of determining TG, namely differential scanning calorimetry, fails because of a couple of reasons. One reason is where the change in the specific heat capacity is very, very small, like you obtain in partially crystalline and partially glassy materials. In these examples, we show that spin probe ESR can be very fruitfully used. So, let me begin a 2-minute introduction to the technique of ESR. ESR is done on samples where you have unpaired electrons, so some net magnetic moments. You place these samples subject to a magnetic field, because of which you have Zeeman splitting of the spin energy levels, and you cause transitions by irradiating the sample with microwaves of appropriate frequency, so that the spins in the ground state go to the excited state, absorbing the microwave photon when this condition, resonance condition, is satisfied. And the typical signals look, this is just an absorption line shape, and due to the peculiarity of the experiment, modulation field and lock-in detection, you get a derivative of absorption as a function of the field. Now, one very interesting interaction that one studies using EPR is the hyperfine coupling between the electronic magnetic moment and the nuclear magnetic moment, which leads to the splitting of the single EPR signal into a multi-component system depending upon the nuclear spin. And this hyperfine interaction we are going to use as a probe to what happens with respect to the structure and dynamics in glasses and supercooled liquids. Now, we are talking about water, and we all know that water does not have any net paramagnetic moment. So, how does one do ESR on water samples? What one does is one dopes something called spin probe or labels or spin traps, which have net magnetic moments, but you dope carefully so that it does not affect the main property of the sample you are studying. You dope it in very dilute way to the concentration of 10 to 100 ppm. So, you just mix the spin probes in water using just physical mixing. So, this is one example of the spin probe we use, Tempol, which has this unpaired electron sitting on the NO bond, and that is the thing we are going to do ESR on. So, this is the sample signal of Tempo, or Tempol signal is similar, and this is Tempo in H2O at a temperature of 5 Kelvin, where you have water in crystalline form. As you all probably know, it is very difficult to make a vitreous water. Invariably, you end up with hexagonal crystalline water, and once you have a crystal, you get a signal of this kind. Without going to the details of the basics of occurrence of the signal, let me say that any crystal does not want to have any impurity in its lattice, so it throws out. So, when the Tempol is thrown out, you get an aggregated ESR sample signal like this, which is an indication of the occurrence of the crystal, water crystal. So, if you see this shape, that means that you have crystalline water. However, if you have a signal of this kind, that would mean that you have amorphous water, vitrified water. This is Tempol signal in liquid water, and this is in amorphous water. Again, the reason for the occurrence of this signal is the anisotropy of the so called G and the A tensors. This is the Zeeman term, and this is the hyperfine term we just spoke of. So, this G and A both are second rank tensors, they are anisotropic, and the distribution in a powder like fashion gives you this kind of signal, which can be taken as the sign that you have formed amorphous water.
What is the meaning of amorphous water?
Glassy water. I am not going to distinguish between glassy and amorphous states here. Vitrified or glassy or amorphous water, I mean the same thing, which is disordered, unlike single crystal. Now, we first did the experiment on like I said polymers, polyethylene glycol 2000, which does not give any glass transition if you experiment it on it using DSC, because it goes into a state where it is partially crystalline and partially glassy, and the change in the specific heat is too small to be detected by the technique of DSC. So, we did spin probe ESR on that and found a glass transition in this sample, and what one does is, let me go back here, one measures the separation between these two peaks. This is the twice the hyperfine coupling constant, Z component of the hyperfine coupling constant. Now, as you have seen here, as a function of temperature, this separation has changed drastically. I measured this separation as a function of temperature and plot as a function of temperature, and you see that there is a very drastic change in the magnitude of this splitting, and this is a consequence of the glass transition. It does not happen at the same temperature as the glass transition temperature, it happens at a slightly higher temperature, but this is a consequence of a glass transition. You can call it so called something like a dynamic glass transition. Now, long time ago, sometime in the 70s, Kumler and Boyer, they have applied this technique to polymers, a number of polymers, and found a correlation between the narrowing temperature and the glass transition temperature. By narrowing temperature, I mean this temperature where the hyperfine separation has reduced drastically from 70 Gauss to about 50 Gauss. They call it the temperature at which the separation has become 50 Gauss, T 50 Gauss. So, they found a correlation between T 50 Gauss and Tg, and this is the sort of plot they get for a large number of different polymer samples. So, now if you use the spin probe ESR technique and find T 50 Gauss, you can extract Tg from the plot. That is the idea. Well, this is empirical relation. There are also some justification why it should happen on the basis of the relaxation time, what it does to the hyperfine separation. There are some 1920 materials here in 1970s. After that, a lot more have been added. So, the data falls roughly on the same graph. You can see the departure from the graph here. So, here we find the glass transition temperature for polyethylene glycol to be about minus 72 degrees Celsius, whereas from DSC you do not get the Tg of PEG. Now, we have applied this to water sample. Now, these two plots are for water and this is for propylene glycol. Propylene glycol we used as a calibration standard for which DSC is known, DSC Tg is known. For water, of course, most of you know there has been a controversy about whether it undergoes a glass transition at all. If so, what is the glass transition temperature? Is it around 135 Kelvin as quoted by some people, or like Professor Angel says, no, you cannot see a glass transition in water. It is preempted because of the crystallization transition. If at all glass transition were to be there, it has to be 165 K. So, what we have done is we have doped little amount of tempol in water and quenched it to 4 Kelvin. I think that is the first time it has been done, quenching water to 4 Kelvin to see if glass forms, and we do notice that glass has formed. You recall this line shape of the spin probe ESR, which I told you is the signature of the glass transition. So, water sample does give this kind of line shape for the ESR signal, and as you warm up the sample around 150 165 K, it undergoes this transition we talked about, sudden narrowing of the spectrum. This is for a quenched sample. This one is for a slowly cooled sample where there is no chance of vitrified water happening. So, here you see that you see one single signal which I showed you earlier as a signature of crystalline samples. So, slowly cooled water ends up in a crystal, fast quenched sample gives you vitrified water. Okay, estimation is difficult, but experimentally what we have done is we have hit the water sample directly with a stream of liquid helium. So, the quenching is instantaneous, but maybe 10 to the 3 Kelvin per second or so. Yeah. Now, this is the standard sample of propylene glycol, which gives the correct Tg as you determine for by DSC. So, this spectra we have analyzed. This is for water, this is for glycerol, this is for propylene glycol. Again, use the Kumler plot to estimate the Tg of water.
So by the way, this is sort of an intermediate cooling rate, right? It's not to be characterized as instantaneous. If you compare to the cooling rates that people in metallic glasses can get up to and need to get up to.
Where they use this spin coating and so on. That's the experiment you are thinking of, where they bring down the temperature from maybe 1000 degrees to room temperature and things like that.
Yeah, the rates are much higher.
Yeah. Here you hit the water with a stream of liquid helium. Yeah. So, this using the Kumler plot we have determined the Tg's of Tg of amorphous water and glycerol and Tg propylene glycol. Now, this is the Tg obtained by our technique. For propylene glycol and glycerol, we obtain literature values obtained by DSC, and this is the value obtained for water. And now, I present some new result.
The value is 132.
For water, it's 132. Yeah.
This is when you warmed up.
That's right. First you quench it and then you warm it. Of course, that's how you observe any glass transition.
No, but sorry, just because. So I thought the issue with this attribution of 136 had to do with what would happen to the state of the glass on different warming rates than the cooling rates. No, this is what Austin had focused on. So even in your sample, this would be the case, right? Because certainly you must be warming it up at a rate that's much different from what you cooled at.
No, there are two comments about this. Austin Angel says that whatever the cooling rate, you cannot, whatever the cooling rate and then warming rate, whatever the warming rate, you cannot see the glass transition, because according to him the glass transforms to the cubic crystalline phase around 160 K or so without going into the highly viscous state that you expect if it had undergone a glass transition. So, that is a different thing altogether.
No, there is a little bit more than that, because the signal that has been attributed to the glass transition is attributed by Austin to a relaxation effect, which happens.
The results of Johari and others you are referring to.
No, it's I mean, what is standard is that if you cool a liquid down at a given rate, it undergoes a glass transition. If you're going to warm it up at a higher rate, it begins to relax below the glass transition temperature that you measure, and this is going to have a calorimetric signature. And so the point is, if what you're picking up is the fact that the liquid is beginning to relax, that's not the same thing as the glass transition temperature. At least we should leave that possibility open, because
the evidence I am providing, the evidence this technique provides, is for the presence of a liquid, not a transition to a liquid, but actual liquid. For example, let me go to this kind of spectrum you can see only in a liquid, and this is the transition region. Of course, glass transition can cover a few degrees in temperature depending upon the warming rate. That is a well known fact. However, here we see the evidence for the occurrence of liquid water. So, that brings me to the present work. This sample is again of water, but in a slightly different matrix. Here again it is quenched to liquid helium temperatures to see amorphous water, but when it is warmed up, you begin to see the signals of liquid water even at much lower temperatures, at 30 K, 40 K and so on, compared to the glass transition temperature of 135 Kelvin roughly. So, this is the new result we have got, and at higher temperatures it again goes through the usual glass transition as we have seen earlier, and this is the signals due to liquid water. And this is the sort of microscopic picture of our sample, where there are pores of sizes varying from nano to micrometers. And my claim is this sample provides an example of interpenetrating or crossing potential energy landscapes, because the different pores have different sizes, different volumes, different number of water particles. So, they have different potential energy landscapes, and when the particles jump from one pore to another pore, they cross one potential energy landscape to another potential energy landscape, and this can lead to a lot many interesting new phenomena so far unexplored. And we guess one of them could be this reentrant glass transition and supercooled liquid phase. This is a classic paper of Professor Shastri, where there is a region identified as landscape influenced region, but I stop here as promised, not taking too much of your time before lunch. And the main conclusion is reentrant glass transition and supercooled state are observed in spin probe ESR experiments on water confined in interconnected regions of nano to micro dimensions, and this occurrence could be a possible consequence of interpenetrating potential energy landscapes of different regions. Thank you.
So, so what's the reentrant glass transition that you
That's right.
talked about?
Okay.
So this we didn't get a clear picture of, I think. But any other questions?
Okay, this refers to this ESR spectra here. Here is one glass transition at a very low temperature of around 30 K, because this is the sign of liquid state. So, this is a signal of glassy water, and at higher temperatures you get a mixture of both this glassy as well as liquid state. This is at low temperature, and if you go to still further temperatures, then again there is another glass transition, another supercooled liquid state. So, there are two glass transitions and two supercooled liquid states. In between the liquid signal goes away. In fact, that is a surprising thing. That is why I call it reentrant. Otherwise, it would have been a mixture of the two things. You might have said that in a very small pore sized material, the glass transition temperature could be different, but it is not so. That narrow signal goes away as you warm up, and then again narrows at a much higher temperature.
Any questions?
Apply here at all, but I mean in thin film, rapidly cooled thin film business, that quite often that this such a phenomena have been seen, and it turns out it was argon mixed up in the film coming out. So there are many examples like that of where, so maybe we have to be careful.
Well, I don't have argon in the sample. That apart, it could be some other impurity. I take your point. Yes, yeah, but true. I mean, we have repeated the experiment a number of times, taking precautions to eliminate presence of contamination or effect of contamination as much as possible.
Liquid signal?
Right. That is consequence of the hyperfine splitting of the EPR signal due to the nitrogen nuclear spin of 1. So, when a nuclear spin has got a value 1, it leads to a triplet of the EPR signal. And in the liquid state, you get a very narrow triplet because all the anisotropic interactions that gives you the broad signal at low temperature, they have got averaged out.
Okay, let's thank Professor Bhat again in view of the time. Yeah, so any further discussions can be taken up privately. So lunch now, 1:30, the second session of the session. And we are back here at 2:30.